Also, the graph of y equals cosine bx will resemble that of y equals cosine x, but it will have a period of 2 pi over b. We not only can stretch or shrink the basic graphs of the sine and cosine functions, but we can also shift these graphs horizontally. Let's look at the following example. Graph y equals sine of x minus pi over 4 and y equals sine x over the intervals 0 to 3 pi inclusive using a calculator. Compare the two graphs on the calculator. All right, so what we're going to do is we're going to go to the calculator, and I've left the previous information in there so I can show you how to get rid of that and how to enter the new information so that you have an example that you can follow to graph these sinusoid curves on the calculator. So let's take a look at that. We would turn our calculator on, hit the Y key, and then what you'll notice on a close-up is that I still have my cosine curve in there. What I do is hit the clear key, and now I can enter sine x, close the parentheses, and then you'll see that printout. Now I can move down to the next line and hit the clear key. Then I would enter my sine key, and then I'm going to enter my x key, minus, and now I want pi over 4, which is second and the little caret, divided by 4, and then close the parentheses. The other thing I want to do is make sure that my window is set, and right now we want to go from 0, so that's okay, and then we want 3 pi, so I type in 3 and the second caret, which gives me the pi. Watch what happens when I hit enter, and that is that it will change to the decimal equivalent. I will leave my x scale alone, and I will leave the y, min, and max alone as well. Let's press graph now, and you'll see on the curve, first it draws the graph y equals sine x, and then it draws the graph y equals the sine of x minus pi over 4. What you should notice on the graph is that the new graph has been shifted to the right by an amount of pi over 4. And that's called a phase shift, where the graph moves left or right, that is horizontally. It's called a phase shift. In this case, when we subtracted pi over 4, then the graph was shifted to the right. When we were to add it, for example, add pi over 4, in that case, it would be shifted to the left. Well, just as we've seen that we can shift the graph of a sinusoid horizontally left or right, we can also shift the graph vertically up or down. So let's take a look at an example of that situation. Graph y equals cosine x, the basic shape, and then graph y equals 2 cosine x plus 3, and y equals 2 cosine x minus 1, over the interval 0 to 3 pi using a calculator, and then compare the three graphs. So let's jump right into the calculator, and we'll take a look at these three equations and their graphs. So we have cosine 2x, 2 cosine x plus 3, 2 cosine x minus 1, and when I hit the graph key, they will be drawn in that order, which is to say, here we have cosine x, next we'll have 2 cosine x plus 3, and then 2 cosine x minus 1. Looking at the graphs, what's happened? Well, the 2 in front of them, of course, changed the amplitude, so they've both been stretched vertically by a factor of 2. But in addition to that, the plus 3 shifted that second graph up. So you can see it's entirely above the x-axis. In fact, what we'll notice is that it has a maximum value at 5 and a minimum value at 1, which the total distance between 5 and 1 is 4, and its amplitude is half that, 2, which is what we'd expect because it's 2 cosine x. Well, what about the graph that's the lowest one on? That's my graph 2 cosine x minus 1. Now, what's happened with that graph is its amplitude was doubled, but then it was shifted down 1 unit. And what that means is that its maximum height, you can see, is a positive 1, and its minimum is negative 3. Well, again, the distance from positive 1 to negative 3 is equal to 4. Half of that distance is 2. The amplitude is 2, which is what we would expect because, again, we have y equals 2 cosine x. So what we found then is that by adding a positive number, we've shifted the graph up. And by adding a negative number, or in other words, subtracting a number, a positive number, we shift the graph down. What I'd like to do for you is formalize what we've just been going over. So what I want to say is we've looked at graphs like y equals c plus a times cosine bx, or we could do it as sine, so y equals c plus a times sine bx. I have a graphic to explain how these work. So let's take a look. Given an equation in the form y equals c plus a times the sine of b times the quantity x minus d, what we know from this is that the amplitude is the absolute value of a. The period is 2 pi over b. The phase shift is d. The vertical translation is c. And our range then becomes the interval negative a plus c, comma, a plus c. And and what I want to say is that we will do an example of this because that was a lot of information jam-packed into one particular graphic. And so let's look at an example where we will apply all of those parts of that formula. Find the amplitude, the period, the phase shift, if any, the vertical translation, if any, and the range of the function y equals 1/2 cosine of the quantity 1/2 x minus pi over 4. And then graph the function over one period. So here I have the equation, and I've also drawn one period of just cosine x. I want to look at the equation first because I need to manipulate this a little bit to put it in proper form. So I write y equals the 1/2 is okay, cosine is okay, but it's this what I need to change. I need to factor out the 1/2 so that the coefficient of x inside the parentheses is 1. And then, because I'm factoring out 1/2, I need to factor out 1/2 from pi over 4, which would leave me with pi over 2. The reason I need to do that is, in terms of figuring out both the period and the phase shift, remember that we factored out the b, and this was x minus d. So, in this case, I can now calculate both my period based on b and my phase shift based on d. Before I do that, let's notice that the amplitude has changed. So the amplitude is 1/2. The period is equal to 2 pi